This is Homeschool 101, a collaboration between ABS Television and the Ministry of Education. Stay attentive and attempt all activities. And now, today's lesson.
Welcome once more to preparation for CSEC chemistry exam. We're now on second part, so we're on Introduction to Organic Chemistry Part 2. My name, once more, is Elton. Now, we want to thank you today for attending our CSEC chemistry class. And we're going to look at organic chemistry, or continue looking at organic chemistry. So a brief definition: organic chemistry involves the study of the sources and nature of the compounds of carbon. So sometimes it's referred to as carbon chemistry. Now, all living things, or all things that were once alive, contain the element carbon. And so that is why it is so important for us to study carbon. Carbon compounds are also known as organic compounds. Now, today we're going to look at homologous series, the characteristics of a homologous series, nomenclature, or how we name our organic compounds, structural isomerism, or alkanes. And note that the formula for the homologous series of alkanes, or the family, homologous meaning family of alkanes, is CnH2n plus 1. Alkenes, CnH2n. Alcohols, CnH2n plus 1 OH, or sometimes just referred to as ROH, where the R represents the CnH2n plus 1 part of the molecule. Carboxylic acids, CnH2n plus 1 COOH, or RCOH. Again, the R here representing the CnH2n plus 1 part of the molecule. We're also going to look at polymers, and then we're going to have a multiple choice examination. So you really need to pay attention today if you're going to pass the multiple choice exam. Now, the Cn here, if we said that N here was 1, then H would have 2 times 1 plus 2, which would be the number of hydrogens. So if this N here was 1, so we had 1 carbon, then we will have 2 times 1 plus 2 hydrogens, which would be 4. Here, if N were 2 here, then it would be H 2 times 2 for N. If N were 2 here, so it would be C2H4, and so on. Right, now organic compounds can be classified into groups, as we said, known as homologous series. The homologous meaning in the same family. So homologous series, homo, same. Logos, the same story, the same family. A homologous series then is a group of organic compounds which all possess the same functional group and can be represented by the same general formula. Some examples, as we said before, would be alkanes, CnH2n plus 2, alkenes, CnH2n, alcohols, CnH2n plus 1 OH, or carboxylic acid, CnH2n plus 1 COOH. Now, some characteristics of homologous series. The members have the same functional group. As mentioned before, they have the same general formula because they're in the same group. The molecular formula then will differ by CH2, 1 carbon, 2 hydrogens, CH2, and a relative molecular mass then of 14. Why a relative molecular mass of 14? The relative mass of carbon is 12. Carbon 12,6, the relative mass is 12 atomic mass units. For hydrogen, it is 1, but if you notice here, we have CH2. So we have 2 hydrogens. So that's 2 times 1, which is 2. So 12 for carbon, 2 for hydrogen gives us a relative mass of 14. Now, members in a series are prepared by the same general method. So all of those in the same family, the same homologous series, are prepared by the same general method. Members in the series possess similar chemical properties. You have to remember that. They all have the same similar chemical properties. The melting points, boiling points, and density increase with the increasing numbers of carbons. So the more carbons we have in the carbon-carbon chains in these homologous series, the higher is going to be the melting point, the boiling point, and the density. And that's because it takes more energy to break the molecules. Now, nomenclature, how do we name these compounds? Straight chain members in homologous series have the name consisting of two parts. So there's a first name, much like we have. We have a first name, and then we have a last name or a surname. Okay, so a common name or a Christian name, and then your surname or your family name. The same thing here for nomenclature of organic chemistry compounds. So straight chain members of the homologous series have a name consisting of two parts. A prefix, so the first part, the first name, the Christian name for us is the prefix for organic chemistry. So the first part or prefix depends on the total number of carbon atoms in one molecule. The second part depends on the functional group. We're going to talk a little more and show you what we mean by functional group in a little while, present in the compounds. Now, each member of a homologous series has a first or common name, as we mentioned before, and a last or family name or a surname, as we mentioned before. Now, how do we then name how do we give this first name, the prefix? Now, it depends then on the total number of carbon atoms in that molecule. Now, if we have one carbon atom, it is meth. So if we hear meth, when we name, if somebody tells you the name of an organic compound and you hear meth, that means that it contains only one carbon. If you hear eth, it means then that it contains two carbon atoms. If you hear prop, it means that it contains 3, bute, 4 carbon atoms, pent, 5 carbon atoms, 6, hex, 6 carbon atoms, hex, 7 carbon atoms, hept, 8 carbon atoms, oct, 9 carbon atoms, non, 10 carbon atoms, dec. So that's how we name them, depending on the number, and this is the prefix, that first name. Prefix, the first name, or the Christian name. It is the prefix, and it depends on the number of carbon atoms. So we're going to use these a lot more as we go through today's study. So we'd like to continue now with the nomenclature of alkanes. And remember, we said nomenclature means name. Okay, so how do we name our alkanes? Now, alkanes, we said, would be CN, H2N plus 2. And they all have carbon-carbon single bonds, so we say they are saturated compounds. These are saturated compounds. They have the maximum number of carbon atoms they can accommodate in terms of bonding. Now, if we were to look at an actual carbon atom, we'll notice that, and here we have a carbon atom, right there in the center of the carbon atom, what we call the nucleus. We have 6 protons and 6 neutrons. Then in the first electronic shell that is orbiting around that nucleus, we have 2 electrons, and the second electronic shell, we have 4 electrons, which gives us a total of 6 electrons. So each carbon atom has 6 electrons around it, but 4 in the outermost shell. So we say it has a valency then of 4. It can form 4 bonds, a maximum of 4 covalent bonds with an adjacent carbon atom, or with other types of atoms like hydrogen. So in this case, carbon-carbon single bonds can form. So if you have 2 carbon atoms, 1, 2, those 2 then can then share a pair of electrons in order to form a carbon-carbon single bond. Carbon, carbon, it's a single bond here, and this is how we depict it, a carbon-carbon single bond. Notice that we have these 3 sticks there, and those represents the 3 extra electrons around each carbon. Okay? And if we were to actually show what it looks like, if we look here, we have 1 carbon, 2 carbons, and here we have those 3 sticks which represent the electrons, and in this case we have hydrogens attached to them. All right, so we're coming back to that in just a little bit, and if we were to look at 1 carbon, we'll notice that it has each one of those 4 electrons in that shell. It can accommodate 4 bonds, in this case hydrogens. Okay, now it means then that we said the prefix, a first name, and then the family name in this case for alkanes would be ANE. So the surname would be ANE, anes. So the prefix, the first name, methane. Methane tells us that we have only 1 carbon atom in this molecule. Ane, ANE, the surname. So meth, the first name, ane, the second name or the surname. Methane. Ethane, 2 carbons. Et meaning 2 carbons, and ane meaning that we have the maximum number of bonds there, hydrogens. Propane, the third one in the series, homologous series. Propane, 3 carbon atoms, and we have all single bonds around it. So these are all alkanes, carbon-carbon single bonds. Okay? Here we have methane. This is what methane looks like. Carbon, 4 bonds around it. 4 bonds around it. Here we have ethane. 2 carbon atoms. 1, 2. 2 carbon atoms. Hydrogen bonds. Maximum number of bonds around it. 6 hydrogens. Okay? All right. Then propane. Then we can have butane. Then pentane. Then hexane. Then heptane. Then octane. Then nonane. Then decane. Depending on the number of carbon atoms that we have. Now, the next group, next homologous series would be the alkenes, as opposed to the alkanes, A-N-E-S. This is E-N-E-S, alkenes. And enes means a carbon-carbon double bond. So we have the alkenes, the homologous series, or the family series, would be CnH2n, carbon-carbon double bonds. Okay? So here again, remember we have a maximum of 4, we can form 4 bonds. So we have 1, 2, 3, 4 electrons around carbon over here. 1, 2, 3, 4 electrons around carbon. And then you'll notice an extra electron here, which is from hydrogen. Another one here from hydrogen. Another one here from hydrogen. Another one here from hydrogen to form the first of the alkenes in the series, or ethene. So again, the prefix et, prop, but, pent, hex, hept, oct, non, dec. But for the first one, ethene, a carbon-carbon double bond. So we have a double bond. This is what it looks like, a carbon-carbon double bond. If you were to look keenly, you would see that we have 2 carbons, a double bond, 1, 2, and then we have hydrogens. So this is the molecule here. This is what it actually looks like. Ethene, propene, propene being 3 carbons, but it must have a double bond because these are the enes, double bond, and then we have single bonds around it. Okay, C3H6, propene, pentene, 5, pent, 5, and we have a double bond, pentene. So this is the family of alkenes. Notice that we don't have, in this case, the maximum of 4 single bonds. We have a carbon-carbon double bond, and then we have 2 single bonds, as opposed to the alkanes. So we say then that the alkenes are unsaturated. Unsaturated, you must remember that. Okay, let's move on. The next one then would be the alcohols. Alcohols, the ol group, OL group, alcohols. So the alcohol will be CN, H2N plus 1, OH. And that OH, or hydroxyl, would be the functional group, or sometimes just commonly referred to as the ol group. So we can represent the CN, H2N plus 1 part of the molecule as R, and then the OH, which is the functional group for the bond. Now the hydroxyl functional group, OH, is in all alcohols. That's how we know it's an alcohol, because it has all of them have a OH functional group. Now this is what the bonding looks like. Carbon bonded to oxygen, singly bonded to oxygen, singly bonded to hydrogen. Again, we use the same system. We have a prefix, and then at the end of the molecule, the surname would be anol. So every alcohol has ANOL at the end of it, and that tells us that it is an alcohol from the alcohol family. Okay, here we have meth, only 1 carbon, meth, and anol, so methanol, the first alcohol. Then we have ethanol, 2 carbons, et, 2 carbons, and OH. Okay, the ol group, OH. So we know this is an alcohol, ethanol. Incidentally, this is the one that we use to make rum. Okay, propanol, 1, 2, 3, 3 carbons, prop, and then anol at the end. So the prefix is prop for 3 carbons. The family name, the surname is anol, so propanol. Okay, let's move on. Carboxylic acids, the next group family we're going to study. Now, carboxylic acids, the formula would be CN, H2N plus 1, COOH. So our functional group then is the COOH group. Again, we can represent the CNH2N plus 1 part of the molecule by R and then add the COOH at the back. We can do that. But the functional group in carboxylic acids would be the carboxyl group. And that carboxyl functional group is the COOH group. That tells whenever you see that, you know that it is a carboxylic acid, or sometimes referred to as an alkanoic acid, or sometimes just referred to as an organic acid. But the correct name would be our carboxylic acids. Now COOH, how does it look? What does it look like? The molecule, carbon, is doubly bonded to oxygen and singly bonded to hydroxyl, OH. Okay? Now that OH part makes the molecule polar. So we have the first one here, a prefix, plus anoic acid when we are naming the carboxylic acids. So the prefix is the first name, the family name is anoic acid. So every one of the carboxylic acids ends in anoic acid. Depending on the number of carbons, we name them. So in this case, we have propenoic acid, because we have a double bond, 1, 2, 3. Over here we have butanoic acid, 1, 2, 3, 4. Butanoic acid, pentanoic acid, hexanoic acid, heptanoic acid, and so on. Okay? And right here we have an example of, let's see, right here we have an example of a carboxylic acid. This one is ethanoic acid. 2 carbons, you can see them, 2 carbons. 1 carbon is doubly bonded to an oxygen, singly bonded to OH. And here we have our 3 hydrogens. Here's the molecule, here's what it looks like. Carbon, carbon, doubly bonded to oxygen, singly bonded to another oxygen, and then a single bond to hydrogen. Another carbon, 3 hydrogens. So this is what the molecule looks like. And we were just speaking about the alcohols, so let's just go back so you can see it. Here we have ethanol. So we have 1 carbon, singly bonded to another carbon. Right here, ethanol. 1 carbon, singly bonded to another carbon. CH3, 3 hydrogens, singly bonded to oxygen, singly bonded to hydrogen, 2 hydrogens. That's the molecule there, ethanol. Okay? All right, let's move on. Now the nomenclature, if we have branch chains, or side chains on our molecules, how do we name them? Now side chains branching off from the longest continuous carbon chain, we call those alkyl groups. The branches, we call them alkyl groups. And alkyl groups have the same general formula, CnH2n plus 1. All alkyl groups have this formula, CnH2n plus 1. They are named using the appropriate prefix and then ending in YL. So the family name there would be YL, il, alkyl, and the prefix would be depending on the number of carbon atoms in the prefix. If it's 1, then it would be met. If it's 2, it would be et. 3, prop. 4, but. 5, pent. 6, hex. 7, hept. 8, oct. 9, non. 10, dec, and so on. But they all end in YL, il. Okay, so the alkyl group. The name of any branch chain molecule has 3 parts that give the number of the carbon atom to which the alkyl group is attached, the name of that alkyl group, and the longest continuous carbon-carbon chain in that attachment. Okay? Now the nomenclature then, how do we name the alkyl groups? As mentioned before, CH3 would be meth. CH3, only 1 carbon, so it has to be meth. And remember, for alkyl groups, we end in YL, family name. So methyl, CH3. Ethyl, C2H5. Propyl, C3. Prop, 3. C3, prop, propyl, C3H7. C4H9, butyl. C5H11, pentyl. C6H13, hexyl. C7H15, heptyl. C8H17, octyl. C9H19 nonyl, C10H21 decyl. Okay? So this is how we name our alkyl groups or attached groups or the side groups or the branched, what we call the branch chains that are attached to our molecules. Now again, let's just go through how exactly we name those branch chains, nomenclature meaning how we name them of the branch chains. The name of any branch chain molecule has three parts. The first part gives the number of the carbon atom which the alkyl group is attached. The second part gives the name of the alkyl group. The third part gives the longest continuous carbon-carbon chain to include the correct prefix. Remember, there's a first name and the homologous series or the family name to which that compound belongs. Okay? Now, we're going to move on then to structural isomerism and then come back to how we name the compounds. Now, structural isomers are organic compounds which have the same molecular formula but a different structural formula. In other words, they have the same molecular formula, the same number of molecules, but how those molecules are arranged in space is different. So we have the same molecular formula but a different structural formula. Structural isomerism then is the occurrence of two or more organic compounds with the same molecular formula but a different structural formula. Each different structural isomer has a different name. So the same functional group indicates the same homologous series, just like we've been doing all along. Okay? So structural isomers of the straight chain molecules can be formed in two ways. We can form those in two ways. One, by the chain of the carbon atoms becoming branched, or by the position of the functional group. So we can actually remove the functional group, change the position of the functional group, and so still have an isomer. So even though we have the same molecular formula, we're going to have a different structural formula, how it is arranged in space. All right, now let's look at a few examples. Here we have butane, sometimes referred to as normal butane. But meaning 4 carbon atoms, and then we have our hydrogens. Now these are all single bonds, if you notice. So this is a saturated molecule. Good. Now we can remove one of these carbons, like over here. So notice that we still have 4 carbon atoms, but we can attach one of those instead of having 1, 2, 3, 4, longest continuous chain. Here we have 1, 2, 3, longest continuous chain, and we attach the carbon on this end right here. You can see that. So even though we have the same number of carbons, 4 carbons, and we have 10 hydrogens here, same number of carbons, we have 4 carbons, we have 10 hydrogens here, so same molecular formula, a different structural formula. And you can see that the two structures are different. Okay? So these are isomers. We call those isomers. And we can say normal butane, and isobutane. Now this is not a very popular way to name it. We prefer the 2-methyl propane. Now why the 2-methyl? Because right here it shows us that if we number these carbons, this would be carbon number 1, this would be carbon number 2, and this would be carbon number 3. And look here, our methyl group is attached to carbon number 2. Carbon number 1, carbon number 2, the methyl group is attached to carbon number 2. So we can say, because it is attached to carbon number 2, it is 2-methyl. Meaning the methyl group is attached to carbon number, this is the methyl group, this is carbon number 2, and we know that the longest continuous chain is 3, prop. Prop would be 3 carbons, ane. So 2-methyl propane, that's how we name it. All right, here we have some isomers of pentane, C5H12. C5H12, here we have pentane, 1, 2, 3, 4, 5 carbons. You can see that. 5 carbons and 12 hydrogens. But we can rearrange this structure. We can still have our 5 carbons and have our 12 hydrogens. Over here, 2-methyl butane. We rearrange the structure. So instead of 1, 2, 3, 4, 5 carbons in the longest continuous chain, we have 1, 2, 3, 4 carbons as the longest continuous chain. We remove this carbon and we attach it here. So now our longest continuous chain is 4 carbons, so butane. But where is our methyl group attached? To carbon number 2. 1, 2. Second carbon. So it's 2-methyl butane. Okay? We could also remove this carbon and this carbon. So we now only have, right here, we can remove this carbon and this carbon. So we now have 3 continuous carbons in the longest continuous chain. And we can attach 1 methyl group here and 1 methyl group there. Now, because both of them are attached to carbon number 2, 1, 2, methyl attached, 1, 2, methyl attached. So we have 2, 2, and because it's 2 methyl groups, we say dimethyl. 2, 2 because this carbon is attached to carbon number 2, this carbon is attached to carbon number 2. So 2, 2, dimethyl, di meaning 2 methyl groups, 2 methyl groups attached to 1, 2, 3, propane. So 2, 2, dimethyl propane. All right? And then we have regular pentane. We could have called 2-methylbutane, isobutane. And when we have them on both sides attached, we can name it neopentane. But remember, these aren't very popular ways of doing it. The required way is this way: 2-methylbutane, 2,2-dimethyl propane. And here we have a few more examples formed by branching. Hexane, 6 carbons. Let's count. 1, 2, 3, 4, 5, 6 carbons in the longest continuous chain. And we can remove this group, CH3, and attach it to carbon number 2. If we do so, it then becomes 2-methyl, because here's a methyl group attached to carbon number 2. So 2-methyl, and if we count the longest continuous group, we have 5 carbons. So that means it is pentane, single bonds. Then we can have 3-methylpentane. So we can move the same carbon, instead of on carbon number 2, we can move it to carbon number 3, which is what we did here. But we still have the longest continuous group being 5 carbons. 3-methylpentane, we can then have 2,2-dimethylbutane, 1, 2, 3, 4. 2, 2 means that each methyl group is attached to carbon number 2. So this one is on carbon number 2, this one is on carbon number 2, so 2, 2, dimethyl, because 2 methyl groups are attached, di meaning 2, dimethylbutane, and then 2, 3, dimethylbutane. So we can attach 1 carbon to carbon number 2, the second one to carbon number 3. So carbon number 2, 1 methyl, carbon number 3, 1 methyl, and because we have 4 carbons in the carbon-carbon, longest carbon-carbon continuous chain, dimethylbutane. And these are all isomers then of hexane. All right, isomers form by changing the position of the functional group. Now, if we were to look at 1-butene, remember ene, carbon-carbon double bond. So here we have a carbon-carbon double bond, but we have 4 carbons in the molecule. So because this carbon-carbon double bond is on carbon number 1, we refer to it as 1-butene. But meaning 4 carbons. You can see the 4 carbons. Ene, double bond. 1, the double bond is on carbon number 1. So 1-butene. Now notice the difference here. 2-butene. We're going to change the position of the functional group. The functional group being the carbon-carbon double bond. In this case, we're going to put this double bond on carbon number 2 instead of carbon number 1. So when we put it on carbon number 2, it now becomes 2-butene. That's how we name them. And then we can have methylbutene, sometimes referred to as isobutylene, cyclobutane. If we remove the double bond, change it, make it a single bond, we have 4 carbons. We still have the 4 carbons, but in this case, single bonds, cyclobutane, and then we have methyl cyclopropane. So we can use 3 of them and attach a methyl group. It then becomes methyl cyclo, cyclo meaning a ring, propane. Cyclobutane meaning a ring, cyclobutane, 4 carbons. So isomers then of butene, 1-butene, 2-butene, 2-methylpropene, cyclobutane, methyl cyclopropane, just like we showed above, but just a different arrangement on the bottom so that you see it better. All right, isomers form by changing the position and have 1 pentanol, in this case an alcohol. All, remember the all groups. 1 pentanol, pent, 5 groups, 5 carbons, 1, 2, 3, 4, 5. So we can count it and see. So we can have 1 pentanol, the OH group, the hydroxyl group, the alcohol group, the ol group, being on carbon number 1. You can see it here. If we move it from carbon number 1 and put it on carbon number 2, instead of 1 pentanol, because it is now on carbon number 2, 1, 2 is 2 pentanol. We can then move it and put it on carbon number 3, as you can see here. If it's on carbon number 3, then becomes what? 3 pentanol. Okay? And then we can have 2-methyl, 1-butanol. So 1-butanol meaning that, butanol meaning ol, 1. The ol group is on carbon number 1. And on the second carbon, we have the methyl group CH3. So because it's on the second carbon, it's 2-methyl, 1-butanol. Over here, 3-methyl, 1-butanol. So we'd expect then that 1-butanol, 1, 2, 3, 3-methyl. On this side, 2-methyl, 2-butanol. So both the methyl group and the ol group is on carbon number 2. So 2-methyl, 2-butanol. And then over here, 3-methyl, 3-butanol. So on, if we were to count, you will see then that 1, 2, 3, 2 ol. On the second one, we have our ol group. And on the third one, we have our methyl group. So 3-methyl, 2-butanol. Okay? All right, let's move on. Reactions then. How do these react? The reactions of the alkanes. Alkanes, remember alkanes are those groups that are saturated. They have a maximum of 4 bonds around the carbon. So our alkanes, saturated hydrocarbons with carbon-carbon single bonds. And here we can see another one, ethane, carbon-carbon single bonds. They have a maximum of 4 bonds around them. Okay, they're saturated. Okay, carbon-carbon single bonds at room temperature. Alkanes 1 to 4 carbon atoms are gases. Alkanes with 5 to 16 carbon atoms are liquids. And alkanes with more than 16 carbon atoms are solids. So alkanes are relatively unreactive, or sometimes referred to as inert. Okay, unreactive, because the carbon-carbon single bonds in their molecules are strong and not very easily broken. These single bonds, because we have the maximum number 4 bonds, and they are arranged at an angle of 109.5 degrees. So it is one reason why the pyramids in Egypt have lasted thousands of years, because of the structure, the way they were built. Okay? Those ancient people were very smart. They figured out that if they have that regular tetrahedron, you know, for the pyramid structure, look at it, tetrahedral structure is going to be very stable, the most stable structure. So that's why they lasted so long. They're not easily broken. All right, now alkanes, there are 2 main types of reactions, or 2 reactions that alkanes undergo. The first one, alkanes burn very easily in air or oxygen. So if we look here, methane, here is methane. This is what it looks like, CH4. 1 carbon, 1, 2, 3, 4 hydrogens. Okay, so methane can react with oxygen or air, or oxygen in the air, to produce carbon dioxide and water vapor, gas. Okay? Now here we have delta H, the enthalpy or the heat, being negative, which tells us that this reaction is an exothermic reaction. An exothermic reaction meaning that it gives off a lot of energy, or it gives off a lot of heat. So we have methane reacting with oxygen to produce carbon dioxide and water. Alkanes can also undergo substitution reactions in the presence of light with halogens. And remember, our halogens are from group 7, fluorine, chlorine, bromine, iodine, and astatine. Those are all in group 7 to produce alkyl halides or haloalkanes. So here we have methane. Methane, that's what it looks like, reacting with chlorine in the presence of light to produce CH3Cl and HCl gas. Now here, this is monochloromethane. So methane reacts with chlorine. The chlorine splits up to give us 2 atoms of chlorine. One of those atoms of chlorine then attaches to, replaces one of the hydrogens in methane, or substitutes one of the hydrogens in methane, and the other chlorine bonds with the hydrogen that is removed from methane. So here we have monochloromethane, And then monochloromethane, mono meaning one, then reacts with more chlorine to produce dichloromethane. Then dichloromethane reacts with chlorine to produce trichloromethane. And eventually, trichloromethane reacts with chlorine to produce tetrachloromethane. Notice that all of the hydrogens in methane, here we have CH4, are now replaced by Cl4, by chlorines. 4 chlorines have replaced the 4 hydrogens. So here we have tetrachloromethane. So these are the 2 reactions of alkanes. Now how do we use alkanes? The uses of alkanes, they're used as fuels because they burn very easily, and as pointed out before, they not only burn very easily, but they also release a lot of energy, a lot of heat. So they're exothermic. So they release a large amount of energy, and that is why our delta H here is saying negative, because it's exothermic. They burn with a clean blue flame, so very little soot. They're easy to store and transport and distribute. Secondly, alkanes are used as solvents because they are nonpolar and are able to dissolve other nonpolar solutes. And then biogas, which is a mixture of alkanes, is a renewable energy source. That's very important now. It's used for cooking, heating, and producing electricity. Okay? Now let's look at the reactions. Let's move on to the reactions of alkenes. And remember we said that the alkenes, the enes, would be the carbon-carbon double bond. And this is what it looks like. 2 carbons, 1 carbon doubly bonded to a second carbon or an adjacent carbon. So carbon-carbon double bond, alkene, ene, double bond. Now remember that because it does not have the maximum 4 single bonds, we say that this molecule is unsaturated, as opposed to the alkanes, which would be saturated because they have the maximum 4 single bonds around them. Okay, so they're unsaturated hydrocarbons because they each contain 1 carbon-carbon double bond, as we just showed you. 1 carbon-carbon double bond. Now carefully, there's a carbon-carbon adjacent double bond and single bonds. Okay, so the presence of this double bond as their functional groups makes alkenes more reactive than alkanes. Okay, because that double bond can then, one of those double bonds can break, okay, to form other molecules. So alkenes, again, they burn easily in air or oxygen. Remember, they have a negative delta H, they're exothermic, they release a lot of energy. Okay, and here we have an example. Ethene, this molecule right here, eth, meaning 2 carbons, as mentioned before. Ethene, carbon-carbon double bond. It reacts with oxygen from air to produce carbon dioxide and water. Alkenes undergo addition reactions. As mentioned, one of these double bonds can break. Okay? So we'll see how they break and what the products are. And when it breaks, it forms single bonds. So alkenes undergo addition reactions with other small molecules to form one molecule. The double bond is broken, and the compound formed is saturated, because then we, instead of having a single bond when it breaks, instead of having a double bond when it breaks, we're going to have single bond. So the double bond breaks to produce single bond. So an unsaturated compound becomes a saturated compound. All right. Now, here we have a few reactions. We can add bromine solution to an alkene. Here we have the bromine. Now this bromine can split up into bromine radicals, Br, so it can break when it reacts. And remember we said one of these double bonds in the alkene will break. So when it breaks, it produces single bonds. And then that bromine, the halogen, attaches itself on either side of where that double bond used to be. So let's check over here. Here we have our alkene. One of those double bonds breaks, so we now have single bond, one single bond left. And when it breaks, it would then attach one bromine atom to both sides of where the double bond was. So we have HH, HH, hydrogens, Br, Br. Now we can use this to distinguish between an alkane, this reaction to distinguish between an alkane and an alkene. Okay? Because whereas the bromine, liquid bromine would be brown, when we add it to an alkene, it becomes colorless. And you have to remember that. That is very important because they can ask you that at CSEC. Okay? We can add hydrogen gas to an alkene. Same thing happens. The double bond breaks. When it breaks, the hydrogens are going to add on either side of that double bond. So this is the result. Same thing happens here if we add steam. Okay, we're going to make an alcohol because steam is water, so it's H2O. So we have one hydrogen, one hydroxyl or OH. And so when that water molecule H2O splits up, we have a hydrogen and a OH, a hydroxyl. And so they add on both sides of what was once the double bond, because the double bond breaks. And that is how our alkenes, that homologous series, alkenes, that is how they react. Okay, by addition. Now, this diagram shows you the different ways to react alkenes, and here our example is propene. So we have one carbon, second carbon, but there's a double bond attached to a third carbon. Okay, so that's propene, and then same thing happens, the double bond breaks. So when it breaks, if we add bromine, the bromine, one bromine would add on either side of what was the double bond. So we have Br, 1,2-dibromopropane. Over here, if we add chlorine, we have 1,2-dichloropropane. Same thing happens. The double bond breaks. Chlorine adds to both sides of what was the double bond. Same thing happens here if we add hydrogen in the presence of a catalyst, nickel, and 150 degrees Celsius. The same thing happens. The double bond breaks. The hydrogen adds to both sides of what was the double bond. Hydrogen, hydrogen produces propane. Here we have propan-1-ol. If we were to add water or steam, a catalyst of phosphoric acid, a high temperature and a high pressure, same thing happens. Double bond breaks, the water, hydrogen, hydroxyl adds on both sides of what was the double bond. Both sides, HOH, so propan-2-ol. Same thing happens here if we were to add hydrogen bromide gas. Okay? Same thing happens here. The double bond breaks, but we can have two products in this case. We can have one bromopropane or two bromopropane, depending on where the bromine from the hydrogen bromide adds across the double bond. If it adds on this side of the double bond, it would be one. If it adds on this side of the double bond, it would be two. So we can have two products. All right? Reactions of alkenes. Now, how do we use alkenes? Alkenes are used as starting materials in the manufacture of many important chemicals because they readily undergo addition reactions. Addition meaning the double bond breaks, and whatever we are reacting the alkene with adds on both sides of what was once a double bond. Okay? So addition reaction adds on both sides. Okay? They readily undergo addition reactions to produce things like ethanol, antifreeze, synthetic rubbers, haloalkanes, and so on. Alkenes also undergo polymerization, and we're going to talk about polymerization just now to manufacture a wide range of polymers, and we call those polymers plastics. So we're going to talk about plastics as well just now. All right, now how can we distinguish between an alkane and an alkene? We mentioned it before. An alkane can be distinguished from an alkene by reacting both with bromine solution. Right? The double bond will break. It will change, the color will change. There will be a discoloration or acidified potassium permanganate 7 solution. Both reactions test to see if the compound contains a carbon-carbon double bond, causing it to be unsaturated. So once we have that discoloration, we know for sure that we have an alkene. In UV light, alkanes cause a solution of bromine to slowly change color from red-brown to colorless. Okay? Due to the slow substitution reaction that occurs. All right, and then we can summarize or tabulate the differences between alkanes and alkenes. The general formula for an alkane, as mentioned before, homologous series, same series, CnH2n plus 2. We know how to do that. Alkenes, CnH2n. So there's a difference. So this is our homologous series, single bonds, double bonds, CnH2n. The type of hydrocarbon, this one is alkanes, maximum 4 bonds around the carbon, saturated. Alkenes has a double bond, so we don't have the maximum 4 single bonds, unsaturated. Now the functional groups, for alkenes, the functional group would be our carbon-carbon double bond, okay, between 2 adjacent carbon atoms. The type of bond in the molecule for an alkanes, single bonds, all single bonds, 4 maximum single bonds. Remember the example we showed you earlier? Methane. Carbon, 4 bonds around it, 4 single bonds. Second example we looked at, ethane. Carbon, singly bonded to an adjacent carbon, maximum 4 bonds around each carbon. Okay? Alkanes. So single covalent bonds. In the alkenes, double bond. Double bond. So we have 1 carbon, a double bond, and then the 2 single bonds. 1 carbon, double bond, 2 single bonds. Okay? So this one, unsaturated. This one, saturated. Okay, so single, 2 single bonds for the alkene attached to a carbon, a double bond between 2 carbons. All right, so single and double bonds in the alkenes. Type of chemical reactions that they can undergo: combustion reaction for the alkanes, substitution reaction, and cracking, which we did last class. And then for the alkenes, combustion reactions. And why combustion reactions? Because they give off a lot of energy. They're exothermic reactions. They produce a lot of heat. Addition reactions in the alkenes because the double bond breaks. We went through that. And then we're going to look at polymerization in a little bit. Reaction with bromine water. If we were to add an alkane to bromine or to acidified potassium permanganate 7 solution, no change. If we were to add an alkene, however, there's going to be a change. Okay? There's going to be decolorization. The brown color of the bromine water, it will change. It will decolorize purple solution in the potassium permanganate. It will become colorless. So there will be a color change. Okay, and that's how we determine the difference between an alkane and an alkene. All right, reactions of alcohols. Again, we talked about this hydroxyl group, OH, as a functional group. All of them undergo similar reactions because they contain the hydroxyl group. The strength of the reactions would decrease as the number of carbon atoms per molecule increases. The alcohols are soluble in water. The water is a polar solvent. Their solubility decreases as the number of carbon atoms per molecule increases. We talked about that before. The more the number of carbon atoms in the molecule, more difficult it is to react. Okay? Again, ethanol can burn in air or oxygen, or the oxygen from air quite easily. It reacts with sodium. So sodium here will replace our hydrogen. It produces sodium ethanoate if we use ethanol and hydrogen gas. We can also produce ethene. We can dry out the water or remove the water from ethanol and therefore produce ethene if we use concentrated sulfuric acid as a drying agent and subject it to 160 to 170 degrees Celsius. Ethanol also undergoes oxidation. So it can oxidize to 2 O's here comes from an oxidizing agent to produce ethanoic acid and water reactions. Okay? Now, orange, the breathalyzer test. The breathalyzer test is what the policemen use to determine if you drank too much alcohol when they stop you on the road. So orange acidified potassium dichromate 6 crystals can be used in the breathalyzer test to determine the alcohol content of a driver's breath. The driver blows on the crystals. If it changes from orange to green, we know that you're drunk. You drank alcohol, you consumed, you imbibed. Okay? So ethanol can be made by using yeast to ferment carbohydrates under anaerobic conditions. Wine is made from grapes, rum from molasses. Now, the reactions of carboxylic acids, the last homologous series that we're going to look at, CnH2n plus 1 COOH. Carboxylic acids are alkanoic acids, as mentioned before. They have the carboxyl group, and we know already they're the COOH. Remember, C is doubly bonded to oxygen, singly bonded to hydrogen. So here we have one of them. Ethanoic acid, 1 carbon, 3 hydrogens. Second carbon, doubly bonded to oxygen, singly bonded to oxygen, singly bonded to hydrogen. Okay, CH3, COOH. All right. So they're polar due to the OH part of the molecule. Like alcohols, the carboxylic acids are less volatile than their corresponding alkanes. They're soluble in water. When they dissolve in water, they partially ionize, and this is how they split up. Here we have ethanoic acid, the one we just showed you, ethanoic acid. Okay? Here we have carbon, doubly bonded to oxygen, singly bonded to oxygen and hydrogen, OH. So right here, this hydrogen splits out. So we have the ethanoate ion and the hydrogen ion. So this H part here is the acidic part of the molecule. Okay? Now reactions, they react with metals. The metals replace the hydrogen. So we have, in this case, calcium ethanoate. Ethanoic acid reacts with metal oxide. Same thing happens. The metal replaces the hydrogen. Ethanoic acid reacts with metal carbonate. So again, the metal replaces the hydrogen. Okay? Now esters. And esters form when a carboxylic acid reacts with an alcohol. It's a condensation type of reaction. We call it esterification. It requires concentrated sulfuric acid and heat. So that concentrated sulfuric acid will remove a small molecule of water. So carboxylic acid plus alcohol produces an ester and water. And in this case, ethanoic acid reacts with an alcohol, ethanol, to produce ethyl ethanoate and water. And we've color-coded these reactions to show you that when writing the formula, the part from the acid comes first, the part from the alcohol comes second, and so when naming, the prefix comes from the alcohol, the il group, and the first part, the prefix, comes from the acid, the anoate part, which is the last part of the molecule. So in this case, ethanoic acid plus ethanol produces ethyl ethanoate. Okay? And one small molecule of water that would have dried out. The sulfuric acid would act as the drying agent. Now, we're down to the last part. Polymers are large molecules or macromolecules. They're made from repeating smaller units that we call monomers that are bonded together. Some occur in nature, while others are synthetic or man-made. The reaction that they're formed from we call polymerization. We have two types of polymerization. One is addition, the second is condensation. Now in addition, it occurs when we have unsaturated monomers, quite like the enes, unsaturated. Okay, carbon-carbon double bonds. One bond would break, okay, and then form chains. So here we have the carbon-carbon double bond. It will break. When it breaks, it forms these two single bonds, and if the N there means we have millions, or a very large number of double bonds. When they break, they produce a very large number of single bonds, so that ethene can produce polyethene or polythene, that twine or string that the fishermen use when they are going to make fish nets. Okay? These are some other examples. Vinyl chloride. We have one chlorine molecule there, a double bond breaks. Okay, so we have many of these repeating units. PVC pipe. This is how it is made. Okay, we have vinyl chloride, and then if we have millions, poly, meaning many, polyvinyl chloride. Okay, styrene. We can have polystyrene. Here we have what the molecule looks like, double bond breaks, single bonds, and we have a long chain of those. These are used to make the food boxes. Okay, those food boxes are made out of polystyrene. The cups that you drink out of, the hot and cold cups, the foam cups, those are polystyrene. And then we can have vinyl chloride producing polyvinyl chloride. We can have tetrafluoroethene producing polytetrafluoroethene. Okay, all of those are polymers or plastics. The second type would be our condensation reactions. So we can have a linking of two monomers in chains by eliminating a small molecule, usually H2O or HBr or HCl, a small molecule. Usually it's water between two adjacent monomers. So for this to occur, the monomer molecules must each have two functional groups, and the polymers that are formed then would be known as condensation polymers. Here we have one producing the amide group. So this one is used to produce proteins. A dicarboxylic acid must be a dicarboxylic acid, 2 functional groups, and a diamine, 2 NH2 groups on either side of the molecule. And then we can produce a polyamide. Okay? So these are some examples. Pterylene, ethylene glycol plus terephthalic acid produces sterylene that makes the fabric that we wear. We use to make cloth. We can also have polyester, a condensation polymer, hexane dioic acid, ethane diol. They condense together. Notice the small molecule that's produced there, and we have a polyester. And we use those to make shirts. Okay, the cloth that makes shirts. All right, we can also produce silicone as a condensation polymer from siloxane. So polydimethylsiloxane will condense, small molecule of water comes off, and we have silicone, condensation polymer. Okay, how do we use it? And we're winding down now. So synthetic polymers or plastics are durable, they're resistant to damage and decay, they're easily molded into many different shapes, they're light and strong, easily dyed different colors, made to be either rigid or flexible. They're good thermal and electrical insulators, easily welded or joined, and they're easily spun into fibers. But then we have a negative side of plastics. Their harmful effects on living organizations in the environment. They're made from non-renewable resources, petroleum. Deposits are depleted. They're non-biodegradable, so they cause pollution. The toxic chemicals are released into the atmosphere and the environment during manufacture of plastics. And then toxic chemicals may continue to be released during use and even after use when we discard these plastics. So there's a good side to plastics and a bad side. Okay? All right, now for the multiple choice exam. Let's look at what a few past CSEC questions look like. So you're prepared for the exam. Question number 1. Which of the following is an addition polymer? Polythene, pterylene, glucose, nylon. And of course it's polythene addition because in ethene, the double bond breaks, forms those single bonds, long chain, polythene. Pterylene can best be described as A, a macromolecule, B, a natural macromolecule, C, a condensation polymer, D, an addition polymer. Of course, the answer is C, a condensation polymer. Third question, which of the following is an alcohol? CH3COH, look for the functional group. CH3CHOH, CH3OCH3, or C2H5COOH. And of course, the key would be, answer would be B, right here. Count the number of carbons, 1, 2, 3. So it's propanol. And in this case, it's 2-propanol, all group. 4, a colorless natural gas decolorizes acidified potassium permanganate 7 solution. The gas is A, ethane, B, ethene, C, sulfur dioxide, D, hydrogen sulfate. Of course, it's B, because the ethene, the double bond breaks, decolorizes potassium permanganate, decolorizes bromine solution. Okay? 5, type of reaction that alkanes undergo. A, addition, B, reduction, C, polymerization, D, substitution. And we know that alkanes undergo either combustion or substitution. So we know this answer is D. Members of a homologous series will all have A, similar boiling points, B, the same density, C, similar chemical properties, D, the same chemical formula. And of course the answer is C, similar chemical properties. Homo, same. Homologous series, the same family series. Okay, 7. That formula is named B, N-propanol or normal propanol, N-butanol or normal butanol, 2-propanol or 2-butanol. Of course, the answer is B, N-butanol. Why but? Because we have 1, 2, 3, 4 carbon atoms, but, and then we have all on that first carbon. Ethanol may be used as a fuel because it has a high heat of combustion, is easily converted to carbon, is easily converted to ethane, has a low heat of formation. Answer is obviously A, has a high heat of combustion. We said that the delta H is negative, it's an exothermic reaction, so we use it as a fuel. 9 and 10, formula for this, what's the name of this formula? A, ethyl methanoate. B, propyl propanoate. C, butyl ethanoate. D, none of the above. The answer is C, butyl ethanoate, an ester. Okay? The butyl part comes from the alcohol part, and the anoate part comes from the carboxylic acid. Carboxylic acids have this functional group. Look at the functional groups. Amine, carbon-carbon double bond, OH, COOH. Carboxylic acids have the COOH functional group. So the key then is D. The answer is D. All right, so that ends our lesson for today. We'd like you to study very hard, eat well, sleep well, stay safe. The good Lord be with you, and thank you for attending today's class.
You've been watching Homeschool 101, a partnership between ABS Television and the Ministry of Education. Thank you for viewing this lesson. Join us again next time.